it is very often the case that the problem changes while we are working on it. We find more out about it and apply already the trial and error method. The other element, which I think is really decisive in something like science, but also very often in some pre-scientific state, is conscious criticism, an attitude of conscious criticism. The beetle doesn't like to err. He doesn't like to move in a direction with his feelers in which there's some hard wall blocking its progress. He has to take this into account, but it isn't the problem. The critical method, the conscious critical method, consists in trying to find whether our hypothesis wasn't perhaps really mistaken. This is now our problem. We have a hypothesis and we find out, or we try to find out, again trial and error, we try to find out its weaknesses. We think about it and think perhaps under such and such circumstances our hypothesis will not work. And then we try to realize these circumstances, make an experiment in which just these circumstances are used, and find in this way whether our hypothesis isn't very weak. In other words, we do lay then stress on the error side of trial and error. Mm-hmm. Conscious stress, we search for our errors. And this is the critical method which exists, I think, only on the human level.
And this is because we, in science, and as you say in other subjects too, we are aiming at the truth. Yeah. And that is our goal. And so yes. I think your view is that we eliminate our errors.
Yes, we aim at the truth, and because we do not fully at once trust ourselves to have really found the truth, we try to eliminate possible errors which would be showing to us that it wasn't the truth. Our hypothesis wasn't true, it was false. So we try really to find the weaknesses of the hypothesis. We try to find out whether the hypothesis isn't false. One can call this attitude an attitude of attempted falsification of our own hypotheses. That is to say, attempted showing that it is false, attempted refutation of the hypothesis. All this is the same thing. So this is really the consciously critical method. It takes not the hypothesis as in the hope just that it will be true, it takes it in the hope that it will be true, but with the determination to test it and to find out whether it isn't false, not to sweep the mistakes under the carpet. But that is really the method which he describes as the normal method. Forget about your mistakes, sweep them under the carpet. Only Kepler didn't do so. That is really... So he wasn't critical of the method he described, because his aim was to reconcile Newton's claims with the fact about Kepler, which Newton had got a little wrong. Mm-hmm. With it, in other words, to reconcile Newton's claim to have proved his laws and his theory by induction, reconcile this with the hypothetical deductive method of conjecture and refutation. Conjecture is the trial, and refutation is the finding of the error. So he does not say we should be critical of our hypothesis. He does not say that this is really the main point in the whole scientific endeavor, to use our criticism. This he doesn't say at all. He does not say that even a well-established theory could still prove one day to be mistaken. He doesn't say that. On the contrary, he believes that a well-established theory is just proved.
I mean, one perhaps can sympathize with him given the tremendous prestige of Newton's theory by the middle of the 19th century.
It was not only prestige, it was a wonderful theory. It was really a theory which, in a sense, survived even Einstein. The Einstein theory convinced me, not because it was so good, but because it could say that all we knew about Newtonian theory and all its successes and all its tests can be used to say that Einstein theory is good and is supported and is successful. Although the two theories were very different, and although the two theories actually contradicted each other, this is very often denied. It is so that Newton's theory very nearly gives the same predictions for observations to be tested by observation as Einstein's theory. The differences are zero for most cases. They are zero if the eccentricity of the ellipse is sufficiently small. They are zero if the velocity is not too big. In both cases, it makes a difference only in the planet Mercury. And there the difference is incredibly small. A few seconds
per century.
Per century. So an incredibly small difference, which is hardly really worth making much fuss about it. So the two theories give almost the same result. However, they still contradict, because the one theory does give something different even a few seconds per century, and it is impossible that both theories should be true together. Einstein, interestingly enough, not only never claimed, like Newton, that his theory is true or proved. On the contrary, at several occasions he did say that his theory will be also only an approximation to a better theory. So Einstein did never claim that his theory was more than a good hypothesis. And on the contrary, I mean, he disclaimed that the theory could be really true. So this is the situation which leads, at any rate, to the result that Kepler's theory consists of hypotheses and not of inductively proved laws, even though they are called laws. Namely, within Newton's theory, the planets attract each other, and by attracting each other, they lead to certain deviations but small deviations of the Kepler laws. So Kepler's laws, which were supposed to be the premises for Newton's law, the inductive premises for Newton's law, are corrected by Newton's law. And this means that you would have to derive Newton's laws from inductive premises which actually contradict Newton's laws, if only a very little. So here there can be no such logical connection between Kepler's laws and Newton's laws, that the one are premises from which the others are derived. Because logically this doesn't work, because they contradict each other. And a similar situation is between Newton and Einstein. Not quite the same situation, but sufficiently similar that we can really say all these are wonderful theories, but they are not proved.
And for all this talk of proof, whether conclusive or inconclusive, you have suggested that we substitute the critical method, a method of, as we've already mentioned today, of applying criticism to our theories. Once we know the theory isn't certain,
yes,
we must always...
We must apply the method of trying to eliminate errors, possible errors. We have to think, where can the theory possibly be false? Under what circumstances could it be possibly refuted? And then we have to try to realize these circumstances and perhaps to hope that in spite of these circumstances it will not be refuted. That may be our personal hope, but what we have to do is to submit it to the severest tests of which we can think. So we have to act as if we were the enemies of our children, of our theories, although we may have personal the hope and even the conviction that they will easily pass all these examinations.
It must say it's this that, of course, it seems to be so much missing from Whewell's view. I mean, the idea that we should positively set out to criticize.
Yeah.
I mean, I'm sure Whewell would have accepted a refutation, a clear refutation of Newton's theory, if it had come. Well, if it had been sufficiently decisive.
If it would be sufficiently decisive.
But he gave the impression that perhaps we should just sit around and wait,
yes,
and wait for the hypothesis to improve up to the level of theory.
Yes. Yes. Anyway, there is this great difference which I regard as the real difference between the human level and the biological level of the trial and error method, the, let us say, beta method level. Or, as I have said, there is only one step from the amoeba to Einstein. Both work with the same method, namely the trial and error method. But there is this one step which makes all the difference. Einstein is critical of his theory. Einstein actually says, I don't think my theory is satisfactory. That he said of his own theory of gravitation. And point out why he doesn't think it is too satisfactory. Einstein spent the whole of his life from producing this theory, his theory of gravitation, the so-called general theory of relativity, in approximately 1916. The whole rest of his life, till his death, which was about 1952, I think.
Something like that.
While trying to improve this theory of his, by trying to find a better version of his theory of general theory of relativity, which was also his theory of gravitation. That is to say, he remained highly critical of his theory all his life and tried to replace it by a better theory. This is an attitude of which the amoeba certainly is not capable. That makes the difference. In other words, the human element in adjusting ourselves to our environment, which is in the main the biological task of science, the human element in it is the criticism, the critical attitude. And it is important to see it must be criticism strictly in the interest of finding the truth, or of discovering falsities, of discovering errors. That is, discover errors, eliminate errors, and thereby learn from your errors and get nearer to the truth. That is the human attitude, and this is only possible for us because we have the human language. The human language allows us to formulate our theories as something outside us, outside our head, something objective between you and me. Here is between us, so to speak, the theory, and here in the book is the theory which we discuss and which we criticize and which we look at as an object and try to improve. Only because we can formulate it in writing or in words, spoken words, better written words, still better printed words. When, with the printed words, they are submitted to a large number of people, each of whom can criticize them in principle. So this objectivity of our theories, the theories may be the object of criticism. This is the great step which the amoeba couldn't make and which, so to speak, Einstein actually